Can you guys see my screen and hear me well? Give me a thumbs up. Thank you. All right. All right, let's get started. Welcome back to Deep Generative Models, Lecture 6. Today we're going to talk more about variational inference, which is that technique that we learned about in the last lecture, which is probably the most scalable modern approach to training deep latent variable models, as we discussed them on Monday. And I call it black box variational inference, because it's essentially, as you understand, it's like a black box technique that, you know, in the sense that you can specify your model and you don't have to worry about any integrals. Right? If you remember in the last lecture, I talked about the fact that in the previous years, when you wrote down the evidence lower bound, there was like a manual computation step where you had to solve certain expectations by hand. And this is no longer needed. So that's why it's called black box variational inference. So for everyone interested in variational autoencoders, today you'll basically learn everything about training such models. And the core piece of that will be the so-called reparameterization trick. Okay. So what do we want to talk about today? As I said earlier, this is about latent variable models, and in particular deep latent variable models, of which the variational autoencoder is probably the most famous representative. I will then talk about black box variational inference and the so-called reparameterization trick, and also about amortized variational inference, which was an idea of speeding up variational inference significantly. Let's talk a little bit more about this idea of latent variable models. So oftentimes we are faced with you know, large data sets of unstructured data, such as, for example, face images. And so there's a lot of variability in X. For example, these faces could be different due to gender, due to eye color, due to pose, you know, hair color, many factors that are just overwhelming to specify. But the problem is that, or the fact is just that in most cases, we don't have like explicit information about it, right? We don't know, we have to detect the hair color, we have to detect the eye color. There's no, you know, information in the image about these all of these different values that would 100% specify a person's face, right? So all of that is sort of unobserved, and therefore we already learned that unobserved parts of a data point can sometimes be modeled as so-called latent variables. We'll call them latent because they're unobserved. Now, the first idea here could be that if we want to build a generative model for images, for face images, for example, we could try to explicitly model all of these factors and then specify a generative process that, based on the values that all of these factors take, would generate such an image. So this is going to be our first attempt to solving that problem. Oops. And just as a reminder, parts of the reason why latent variables were so powerful is that they can be essentially thought of as, you know, or causing very high dimensional mixtures. They correspond to mixture distributions in some very high dimensional spaces. So what you see here as a reminder was like just a mixture of 3 different Gaussians, as you can see here as the blue curves. And if we sort of ignore which Gaussian component is responsible for a given value that the density takes, right? If we're just summing over all of these 3 individual Gaussian densities, then we get the red curve, right? The envelope. And this, as you see, is just like something highly complex, something highly expressive that we could never realize with a single parametric distribution. And we get this by just taking that adjoint model over both data X and latent variables, and then summing over all of the values that these latent variables take. Right? In this example, it would be the Gaussian means, the Gaussian variances, but also the latent variable that decides which of the 3 different Gaussian components a given data point belongs to. All right. Okay. Okay, so essentially by deep latent variable modeling, we should be able to learn highly expressive distribution over complex data, such as images. And here's a model, or here's an example of how this could potentially look like. Right? So this is supposed to be a generative model over images. Its structure is just shown on the left-hand side, where a solid white nodes, as here, illustrate latent variables in this graphical models notation. And shaded nodes, as here, are observed variables, such as the data, right? And then there's an arrow going from z to x, expressing that x is modeled based on a value that z takes. And in the example of images, it could be a diagram that you see on the right-hand side, right? So we could, we want to model the image. That image depends on the gender. It also depends on the pose. It depends on eye color and hair color, which in turn could be influenced by ethnicity and so on, right? So we could get the idea of sort of trying to manually specify such a generative process of the data. Yeah, and if the latent variables are chosen properly, then it turns out that even though that P of X can be really difficult, we could actually achieve to model P of X with relatively simple building blocks. So every X condition on Z could be a relatively simple probability distribution, as in the Gaussian mixture model. Yeah, and if we had trained this model before, we could then actually identify the features in the image by looking at these posterior distributions, P of Z given X, right? So those would then essentially serve as, if you will, detectors of the image, right? By sort of flipping the probability from X given Z to Z given X, you're now able to infer these latent variables from the image. For example, you could detect the eye color, the gender, and so on, right? So you would kind of automatically get these distributions. Sure. All right. Yeah, but the challenge is that actually it's very difficult, right? I mean, it's very difficult to come up with a realistic generative process of the data based on these observations. Is that fine? Is that distracting anyone here with these? Oh yeah. Oh, good point. All right, maybe just move it here. Okay. All right. Okay. So what is then the variational autoencoder doing? It's essentially a similar idea, but we're modeling now all of these latent variables much more in a black box fashion. In the following sense, we still have a generative model over images. We still have the same structure going from Z down to X. But as you see here, there's a bunch of nodes responsible for explaining the image. All of these are latent variables, but they're all densely connected to the observed data, right? In fact, there is a neural network mapping going from Z down to X, right? And just by pushing these sets of latent variables through the neural network, you're sort of simultaneously generating all of these individual pixel level observations. So this can be expressed in the following graphical model or generative process. First of all, you sample Z, the latent variable, from some prior. We oftentimes like to work with simple normal distributions. So this would be just normal 0, 1. And then conditioned on the value that Z took, we then define our likelihood model, P of X given Z, again as a normal distribution. Right? I mean, first of all, this sounds super simple. I mean, it's almost incredibly simple. How could you ever model a distribution over images just working with Gaussians? But the important thing here is that the mean and the variance of that normal distribution of P of z given x are actually nonlinear transformations of that latent variable z. In fact, mu theta of z is a neural network, right? That goes from that takes this random vector z as an input and nonlinearly transforms it. And similarly, sigma theta of z is also a neural network that converts the same latent variable z into a corresponding variance. And even though both the likelihood P of x given z and the prior P of z are extremely simple, because we used neural networks for these intermediate nonlinear transformations, the marginal distribution P of x, where we integrated over all possible realizations of z, can then be actually highly complex and very expressive, and is in fact able to model these complicated distribution over natural images. Okay. Yeah, so we talked about latent variable models, which allowed us to define complex distributions, P of x, importantly based on simple building blocks, right? The only thing that we needed here were Gaussian distributions and nonlinear transformations. And they're pretty natural for unsupervised learning tasks, such as, for example, clustering or representation learning or nonlinear dimensionality reduction, these kinds of things. But oftentimes the cons of latent variable models is that they're more difficult to learn, right? And in fact, that was basically a large part of the last lecture, and we'll even need another lecture today just to explain how you train these deep latent variable models and how you compose models based on them. So a little bit more complicated. So definitely more complicated than autoregressive models. And yeah, and that's it. Any questions so far? Okay. All right. Let me actually recap a little bit more because we'll kind of draw heavily on all of these concepts again. Just to remind you of the idea of variational inference. What was variational inference? So the main idea was that it is an approximation technique for doing Bayesian inference in complicated machine learning models. So for example, imagine that you want to infer the so-called Bayesian posterior distribution, P of z given x, for a latent variable model. In general, we learned that this is oftentimes a complicated multimodal distribution. And just as a toy picture here, I chose this sort of bimodal black distribution that you see here. Instead of exactly computing it, we're choosing a so-called variational family, Q of z given phi, that has certain so-called variational parameters phi. And we're tuning then these variational parameters phi, for example, the mean and the variance of a Gaussian distribution, such that we match as good as we can the variational distribution to the posterior. Right? So in this case, you would get the matching between this simple dashed Gaussian distribution here to this bimodal posterior. And the objective function that we minimize is in fact the KL divergence, the Kalber-Gleitler divergence between Q and the posterior. And we learned it was actually equivalent to something that almost looks the same, but has a different sign. And it also did no longer depend on this posterior normalization constant P of x anymore. And that thing was the so-called evidence lower bound, or ELBO. And it was defined as the expectation under Q of the log joint distribution, which we assume we know, minus log of Q. Okay. All right. We also talked about marginal likelihoods, and in particular, their relevance in learning models over only partially observed variables. Right? So for example, think of handwritten MNIST images that are partially occluded. So we just don't know the values of these pixels in the top part of the image. And then in this interpretation, X could be the observed part of the image, and Z could be interpreted as the unobserved part, right? The top part. Suppose we want to learn a model over these images still in the presence of this missing information Z. What we could then do is we could still use the maximum likelihood training paradigm. And we can only, because there's some part of the image that we simply don't have access to, the most natural thing to do is to aim for maximizing the so-called marginal likelihood. right? Which is P of X independent of Z, right? Summing over all possible completions of the image and still trying to maximize the likelihood of the observed part of the image. Yeah, so this was then kind of the summation over the joint distribution and summing over all Z's here. And as we also learned that this essentially amounts to, assuming a priori any possible way of completing the image and summing over all these probabilities. Okay. We then talked about this training algorithm called variational expectation maximization that still allowed us to train a probabilistic model in the presence of these latent variables Z. And that drew heavily on this evidence lower bound again and on the KL divergence. Just as a recap, the KL divergence between the variational distribution Q and our posterior P of Z given X is given by, can be written as such. And we learned that this is always non-negative, right? KL divergences we actually proved could never be negative because it's in some sense a distance measure between distributions, and we asked that distance measures are never negative. We also learned that this is actually a lower bound to this marginal likelihood. We could actually prove that log P of X is always larger or equal than this thing that we call the elbow, evidence lower bound. And here it is once more written as an expectation under Q of that log joint distribution. And then the other term was actually an entropy term, right? Expectation of log Q under Q is exactly an entropy of that Q distribution. It turns out that both are equal if Q is exactly the posterior. You can easily verify that because in this case, the KL divergence is exactly 0 if both distributions are equal. And then you can show that on the right-hand side, this also has to be 0. And this exactly tells you that the log marginal distribution equals the elbow, right? So in other words, this lower bound becomes tight if Q equals to P. Yeah. And we also argued that because we simply did not have access to log P of X, right? Because it was dependent, we simply could not perform the exact summation over the latent variable Z. The next best thing that we could then optimize instead was this evidence lower bound, right? Because if we kind of maximize the evidence lower bound, we always know that we sort of simultaneously maximize a conservative estimate of the log likelihood of the model. Right? So the likelihood is actually always larger. So by maximizing the evidence lower bound, we automatically sort of maximizing also the likelihood of the model. At least that was the hope. Okay. Yeah, we also talked about variational distributions over images. This actually typically amounts to making a choice of what Q distribution I pick. And we learned about the fact that for example, for image completion, as you see here, for a given specific image X, a typical choice then would be to say that the variational distribution factorizes over all image dimensions, right, over all pixels, or in particular the pixels that are occluded, so over all unobserved variables Zi, and then essentially modeling them as a Bernoulli distribution. The Bernoulli distribution is, again, a binary distribution over 0 and 1, where the Bernoulli parameter expresses the probability of one of the two outcomes, which is phi. And this is then exactly the expression of the Bernoulli distribution. Yeah. All right. Yeah, that was a very long recap, but I fear it's important because we'll just kind of stay on this very deep technical level and just carry on a little bit more, because so far we haven't really understood how you optimize these evidence lower bounds, and that's exactly what this lecture is about. The previous lecture was essentially only about definitions. Now we really learn about how do we actually take gradients, because in machine learning when we fit models we take gradients of some loss function. Right? How do we build gradients with respect to this evidence lower bound? Okay, but are there any questions so far? All right. Yeah, feel free to ask at any point. Okay. Yeah, so let's talk about this black box variational inference technique that again allows you to compute this, not only write down this elbow, but actually optimize it. So here it is once more written. So this elbow depends on the data x, and it depends on the model parameters theta, and it also depends on the variational parameters phi. And here it is once more defined. The expectation is over Q of z with parameters phi. And then we have the logarithm of the joint distribution involving the model parameters theta. And then this entropy term, which again only depends on the variational parameters phi. Now, the first question is, how do we actually even evaluate this evidence lower bound? It still has like this abstract form, right? It's written as an expectation. If you really want to know the numerical value of this thing, given a set of parameters phi and theta, how do we even get its value, right? How do you even evaluate it? And even that is not completely trivial because we cannot compute these expectations analytically. And so we have to approximate them using Monte Carlo sampling. So what do? We use the fact that we get an unbiased estimate of that evidence lower bound by simply sampling a lot of times from that Q distribution, Q of z. So now we have z1 through zk, which are samples from Q. And now, as in other Monte Carlo estimation techniques, we're just kind of evaluating the argument of this expectation over these samples, zk. And then we're building the empirical average. So just evaluating log p, the joint distribution minus q over zk, summing over all possible k, and then dividing by capital K, which is the number of samples. Yeah, if we sample often enough, this kind of gets us a less and less noisy estimator of the elbow slip value, right, for a given set of parameters. The key assumption here is that the Q distribution is actually relatively simple. And that actually means that we don't have to worry about sampling from it, right? There might be other cases where even sampling from Q is difficult, but here, for simplicity, think of a factorized Gaussian distribution. We know how to sample from products of Gaussian distributions. Oops. But now we get to the next challenge. We've just learned about how to even just evaluate this evidence lower bound. How do we optimize it? Any ideas? Mm-hmm. Yep, it's basically the same idea. So essentially, the idea would be to first of all estimate it, as we did here, and then just simply taking the gradient of that estimate. And in some sense, this is exactly the answer if we talk about the model parameters theta. So I'll show this to you in a moment. So remember, we want to both optimize the model parameters theta and also the variational parameters phi. Turns out one of them is easy, the other one is more tricky. If we only care about the model parameters, the answer is exactly as was given here in the lecture. The gradient can be estimated by just, first of all, estimating the value of this evidence lower bound by sampling from Q, and then taking the gradient of that estimate. So in other words, the exact gradient of that elbow with respect to theta, and I'm highlighting them here in blue here because later phi is going to be red to make it more visible. All I do here is I exploit the fact that the expectation is a linear operation, right? So building the expectation is linear. And so I can pull in this gradient into that expectation. And now essentially this is then the same as just if I do this Monte Carlo estimation, then all I have to do again is I sample from Q multiple times. Now I could collect all of these terms, P of zk, and I build their sum and I differentiate each and every one of them, right? And I'm sort of building the average of these many terms by dividing by 1 over k. Okay. So this is good news, right? I mean, pretty simple. We just are allowed to exchange the expectation with taking the gradient, and we can still do our Monte Carlo trick to get a gradient of this evidence lower bound. Now, this gradient turns out to be not the exact gradient, but a noisy realization of the gradient. Essentially, the noise comes from the fact that these samples are random. But it turns out it's an unbiased estimator of the gradient. And so on average, that stochastic gradient will actually show into the right direction. And this is exactly what you need in order to converge. Right? So everything is good. But now we actually get to the more tricky part. We also have to take the gradient with respect to these variational parameters phi. And this turns out to be slightly more tricky. And there are essentially two big ways of getting that gradient. One is called the so-called reparameterization trick that we will talk about in this lecture. And another trick is called reinforce, which has to do with reinforcement learning, which is slightly more general, but oftentimes not as good. So it turns out that this reparameterization trick is very important. So first of all, what's the problem? So the problem is that if I now take my elbow and I want to differentiate it with respect to these variational parameters phi, I encounter the following problem. Or first of all, can somebody point out the problem? So what's sort of different or what's more complicated this time? Yeah, there's a question. Yes, so the sampling distribution depends on phi. That's right. And can you explain more why that's a problem? Yeah. So the answer is right. So basically, the idea is that ultimately we want to do Monte Carlo sampling by creating samples from Q. But now the Q distribution itself has parameters phi, and we want to differentiate it with respect to phi. So it's sort of not completely clear how to do that, how to differentiate the distribution from which you want to draw these samples. Right? It's essentially not clear how the gradient backpropagates through that operation. Right? Oops. So we still want to somehow work with Monte Carlo estimates because we think it's a good idea. It's the only way to deal with these expectations. But how exactly do we do that? Yeah, and later on, we'll talk about this reinforced gradients, which are an alternative. But for now, we'll talk about the so-called reparameterization trick. Okay. All right. So I want to first explain this problem or the solution to it on a slightly more general setup, which actually has sort of a cleaner notation. I don't want to kind of unnecessarily blow up the notation to keep it simple. And what I do here is I want to consider a slightly more general problem, namely assuming we have some function of phi that is given by the expectation under a distribution whose parameters depend on phi of some other function r of z. And I'm interested in taking gradients with respect to phi of this thing. So this is clearly a generalization in some sense of what we've seen before, right? So r of z would be actually the argument of the elbow, which contains these two logarithms. So this just looks cleaner. But it's also a simplification because remember, r in general also depends on phi. But here we'll kind of abstract away from that problem for a moment. Yeah, and that expectation is given as an integral with respect to that Q distribution, and then the argument again of that integral is r of z. We integrate over z. We assume that z is continuous, which is sort of essential in this reparameterization trick. So the question is then, how do we actually obtain a Monte Carlo gradient estimator if Q itself depends on phi? And this leads to the idea of reparameterization. And it's actually the easiest to understand if we make a further simplifying assumption, namely that Q is in fact a Gaussian distribution. Right? It turns out that this is actually oftentimes the case. It's just like a very convenient modeling assumption to let these variational distributions be Gaussians. It's not strictly required, but for now, let's actually assume that Q is Gaussian. In other words, it has like a certain mean mu and a certain standard deviation sigma. So the variational parameters, therefore, are just mu and sigma, right? Because those are the tuning parameters of a Gaussian. Okay. Now, it turns out that the following identity holds, and this will be very important. It is exactly the same if I say I sample z from that Q distribution, Q of z, which was a Gaussian distribution with mean mu and standard deviation sigma, or if I say I just realize my random variable z differently. First, I sample a random noise epsilon from a standard normal distribution centered around 0 and with variance 1. And then I'm just rescaling it to match that original distribution. In other words, I'm shifting that random variable by mu, and I'm kind of scaling that variance, that noise variable by sigma, by the standard deviation. So if I do that, I get exactly the same, I get equivalent samples from Q. Right? So those steps are completely independent. And in fact, this is actually how samples from Gaussian distributions are realized, right, in the computer. Okay. So I want to consider a slightly more general setup. Namely, I want to call mu plus sigma times epsilon. I want to also call that g of epsilon with parameters phi. So this is in this case, a simple scale and shift transformation of epsilon. And it depends on these variational parameters phi, which were again mu and sigma. So I can just call this here g of epsilon and phi. So now using this equivalence, we can actually now compute the gradient of that expectation using the following reparameterization trick. Right? Reparameterization exactly refers to this idea. So just copying that expression, expectation under Q of R of Z, equals then the expectation under that noise variable, sigma, which is now standard normal distributed, of R evaluated of G of epsilon and phi. Right? So instead of sort of integrating over the original Gaussian random variable, I now integrate over a standard normal distribution, and I'm just kind of rescaling that, these samples according to G. Okay. So far, it's not clear how this is useful, but you'll understand that in a moment. Is so far everything clear? All right. So how is that useful then? Well, first of all, this is another way how to write it. I can call it P of epsilon, which is this Gaussian noise variable, and then R evaluated in mu plus sigma epsilon. Now, it turns out if I want to compute the gradient, if I want to solve my original problem of computing the gradient with respect to phi of this expectation of R, this is once more this equivalent expression. But now observe that I can now actually interchange the expectation step from computing the gradient. In other words, because that epsilon distribution is now independent of phi, I can now pull the gradient inside of that expectation. And now with this expression, we know very well how to handle it. Somebody knows how to handle that remaining expectation? Monte Carlo, yeah. It's a great general answer, Monte Carlo. Yeah, Monte Carlo is the solution. So you just sample multiple times this random noise variable epsilon, and then you plug these epsilon values into that expression, and you take the average. Yeah, so this was like the trick, right? And now with this trick, which is called reparameterization trick, we're actually able now to differentiate the elbow with respect to these variational parameters phi. Okay. So importantly, so to think about it is as follows. You first create a fixed realization of these noises. So when you kind of, when you implement this algorithm in a computer, you would first generate epsilon 1 through epsilon k by sampling them from a Gaussian distribution. And then you would kind of put together this objective function, as you see here. This gives you like a sum over k terms. And then every term is just differentiated for a fixed epsilon. So now what remains is really just like, there's no more randomness in there. It's just like some function of phi that you differentiate. Yeah, so for fixed epsilon, this is just a function of phi, and we just compute the gradient by standard backpropagation. Right? Remember, we still probably have some neural network architectures built in there somewhere, and so we'll use backpropagation to compute the gradient. Yeah, there's a question here.
Epsilon just comes from any constant distribution.
In general, it can come from any constant distribution as long as you know sort of a good, as long as you know this reparameterization mapping from that distribution to your target distribution. Yeah. Yeah, there are generalization schemes of that to working with different than Gaussian distributions. Yeah.
Is there any advantage to, because you can get to Gaussian from some other distributions, like sample from a log Gaussian,
Mm-hmm.
and then find exponential. Would that lower your variance, or is it all?
Good question. So the question was sort of, can we pick these noise distributions more cleverly such that the gradient estimator has a lower variance? And I'm sure it's possible in general, but actually oftentimes in practice, it turns out that these Gaussian posteriors have a very small variance already. So oftentimes actually it turns out that variance is not a huge deal in these reparameterization tricks. So in fact, oftentimes we even draw only a single epsilon, right? So k equals 1, right? So oftentimes a single noise variable is enough to optimize your evidence lower bound. But that's, of course, just like an empirical observation. Right? It's nothing fundamental behind that. Yeah, another question?
Is R just an arbitrary function that will
Right. For now, R could be any general smooth function, but later on, R will be the log joint distribution minus log of Q, right? Because then this expectation here will become exactly the evidence lower bound. And that's actually the next slide. In practice, we want to do that to the elbow, right? We were interested, the whole reason why we discussed it was we want to differentiate this evidence lower bound with respect to phi. Here it is given once more. And so you then recognize that if you just call this argument here R, then we've just sort of solved the problem. We almost solved the problem. There's a tiny difference that I mentioned a few minutes before. Namely, this R here is no longer independent of phi. Right? Previously, we assumed that R is independent of phi, just to make it simpler. Here, phi still enters through this log Q expression. But there's a very simple fix to that. And essentially, you can still do the reparameterization trick as before. And you still reparameterize Z. And the only difference, if this here also depends on phi, nothing really changes, right? I mean, so now we can still write this expectation with respect to that noise variable that no longer depends on phi. The argument is now this generalized R, but you can still sort of approximate it by samples, and you can still compute the gradient of it. So there's really no big difference. Okay, any other questions or comments? Yeah, so I guess if you see that for the first time, it can be a little confusing, but it's I would say it's really important. It's probably the most important thing to know about variational autoencoders. And maybe you want to just revisit that lecture or just look again at the lecture notes. But there's really nothing magical behind it. It's relatively simple math. Yeah, there's a question here. Oh, I'm sorry. Yes. Unfortunately, I was having a hard time understanding your question. Could somebody maybe try to rephrase the question, or do you want to ask once more?
I was just asking if Z is equal to mu plus sigma epsilon.
Yes.
Would QZ equal P epsilon?
Oh, you mean? Yeah. So Q of Z would be equal to P of epsilon if mu was 0 and the scale sigma was 1, right? So in other words, if you did a trivial transformation, you didn't do the shift and you didn't do the rescaling, right? So Q would be already a standard Gaussian. Yeah. Mm-hmm. All right. Okay. Yeah. There's one more important extension here that relates to training models on very large data sets. And this has something to do with stochastic optimization. As you all know, stochastic gradient descent is very important for deep learning. Without stochastic gradient descent, we typically couldn't train any models on really large data sets. And it turns out that in the context of variational inference, that you have to think about that a little bit, right? And there's a technique called stochastic variational inference, which essentially integrates stochastic optimization with variational inference. And we'll talk about that in the next few minutes. So remember that whenever we talk about the log marginal distribution, which is lower bounded by this elbow, it is actually really a function of all the data, right? It really is an expectation over all data points. In other words, we have a loss function, which depends now on the data set and the parameters. And we sort of typically want to average the log likelihood over all data points from our data set. Now, you can still lower bound each and every individual term, as we've seen here. So, and this then kind of gives you just like a sum over all sorts of different elbows, right? Where every individual elbow term depends only on one data point xi. It's the most natural thing that you would expect. Now, importantly, in general, these variational parameters phi I are also specific to individual data points, right? So think of this image completion example. If a certain part of an image is occluded, you want to specifically model that part of that given image. And so your variational parameters should better be specific to that given data point. So that means that phi actually has this index I. It's really a per data point variational parameter. Yeah, and for that reason, this following quantity holds, the inequality holds, that namely that this, when you try to maximize the average empirical log likelihood over the model parameters phi, this quantity is still lower bounded by the maximum over all model parameters theta and all data point specific variational parameters phi 1 through phi m, and then sort of averaging these elbows over the data set. How can you now combine variational inference with stochastic optimization? In other words, with subsampling individual data points from your data set. It's basically a relatively simple trick. You want to optimize this averaged elbow over the data set as a function of phi and over these many individual variational parameters, phi 1 through phi m, using gradient descent or stochastic gradient descent. Here it is written out once more. And the algorithm would essentially proceed as follows. You initialize all of these parameters, and you randomly select a single data point from your data set, as you do in stochastic gradient descent. And then the first step is to actually optimize your evidence lower bound over the variational parameters for this specific sample data data point. So you look only at L of xi, theta, and phi I, and you first maximize it with respect to phi I. This can oftentimes be done with gradient descent, and we just talked about it, right? You kind of, this is where, for example, reparameterization kicks in. You just kind of run this gradient descent procedure, and you run it until convergence. And remember that you didn't change theta. Theta was supposed to be given. And after a couple of steps, then you have like the optimized variational parameters phi I. Now the trick is that you now compute the updates of your model parameters theta. And because you subsampled only a single data point, which is enough in stochastic optimization, you also need to know only one optimized set of variational parameters, namely only those belonging to that data point. In other words, you only care about phi I optimized, right? And now essentially, based on that optimized phi I and data point xi, you can now compute the gradient of that data point. This is enough to kind of give you a noisy estimate of the total gradient of your loss function. Now, can anybody say why this might be sort of a slow algorithm in practice? Even though you sort of already subsampled data points, but why is it still slow? Yes, exactly. You have sort of two intertwined optimization loops, right? You have the outer stochastic gradient steps, And then for every single data point that you subsampled, you still have to carry out an inner optimization procedure. You have to fit for that given data point, you have to fit variational parameters phi I, right? And typically kind of intertwined optimization algorithms tend to be very slow, and you want to avoid them at all costs. You need, for example, 2 different stopping criteria and things like that. Now, how do we improve over this? And that actually turns out to this to link to that concept of amortized inference that I talked about before. The idea of amortized inference is to exactly avoid this double loop structure. In some sense, you want to get rid of local variational parameters phi I, which are again data point specific variational parameters that you have to optimize for each and every data point. So far, we just, by definition, we had these per data point variational parameters phi I. So can we maybe just completely get rid of them? Yes, because this doesn't really scale to large data sets. And this now links to this idea of amortization, which is to say that we get to learn a single function f that has now its own parameters lambda that actually tries to predict the optimized variational parameters of every data point xi based on the features of xi. In other words, we're trying to regress for every data point xi. We're trying to use the features of xi to automatically predict what that data point's optimized variational parameters phi I would be. Right? And this involves another network, a neural network, which we call f lambda. For example, if q of z given xi are Gaussian distributions with different means mu1 until mu_m, one mean for every data point, then we can learn a single neural network mapping that takes the data as inputs and predicts just the mean of that variational distribution. Yeah. Yeah, the question was, why does every xi need its own set of variational parameters phi I? This is actually not generally the case, but oftentimes. Many deep latent variable models that we'll care about, like variational autoencoders, just have that structure that essentially every data point has their own sets of latent variables. So for example, think of the variational autoencoder. So there, the idea is that you have every data point is generated by first sampling a noise vector and then taking that noise vector and sending it through a neural network. And that then generates your data point. So that noise vector would be that data point specific latent variable. And in order to learn it, in order to do inference, you really need to have tuning parameters specific to that data point. So it's not generally true, but it's true for a lot of models that we care about. Yeah, there's another question here. Exactly, that's a good answer. The posterior distribution q of zi given xi would be a totally different distribution for every data point. And we want to match each and every individual posterior. And so the variational parameters also have to be specific to the data points. Yeah. Should it be the case for every model? No, there are many exceptions. For example, if you think of simple matrix factorization models, for example, a data point is typically considered to be an individual user item interaction, like a click or like an entry in that matrix, right? And here we don't have the concept of per data point latent variables. Rather, the latent variables would be actually the model parameters themselves, and they're in some sense shared across the data set. Also, there are many other models where, in time series models, you want to do inference over shared model parameters that are the same across every time step. Also, in this case, you wouldn't have that. You might have latent variables that are not specific to individual observations. Yeah, oftentimes it's a mix. You oftentimes have per data point latent variables, and then you have global latent variables. Mm-hmm. Okay. But let's get back to this idea of amortization. So the idea is, again, we want to avoid the double loop structure of stochastic variational inference that we discussed before. And instead of optimizing per data point variational parameters phi I, we're predicting these optimized variational parameters phi I star based on features of the data xi. And this now replaces the variational parameters phi I by a global set of variational parameters, which are now what? What are the new variational parameters? Sorry?
A single pipe network which like the parameters of that lambda.
Yes, parameters lambda. Okay, good answer. Yeah. So the neural network parameters lambda essentially become the new variational parameters. Yeah, and they're now global. They don't depend on individual data points. Yeah. All right. So we approximate the posteriors using this Q lambda distribution, and lambda are now these amortized inference, these network parameters of this so-called amortization network or inference network. Okay. And now the nice thing is that this really eliminates this expensive double loop structure. We can now actually re-express the elbow as follows. So first of all, here's kind of how we got to get to know it, right? This is kind of how the elbow looks like as we learned about it. But now phi is actually has a different meaning. Phi now are these amortized inference parameters, which are no longer depending on individual data points. And in some sense, phi and theta now become much more on par with each other. The whole expression looks much more symmetric in terms of phi and theta, in the sense that you can now jointly optimize the elbow over phi and theta. So the idea now would be much simpler. You initialize the model parameters theta and the amortized inference variation parameters phi in the first iteration. Now you randomly sample a data point from your data set. Now, usually you would have to optimize that data point's variational parameters. But now the nice thing is you can simply differentiate that new evidence lower bound with respect to both theta and with respect to phi. So it's very symmetrical in theta and phi. And then you just do a single update step on theta and phi as you do in stochastic gradient descent. So how do we compute gradients? We just use, again, the reparameterization trick that we already learned before. Okay, any questions again so far about amortized inference? It's essentially synonymous to the variational autoencoder, as you'll see in a moment, because the contribution of this variational autoencoder paper was twofold. First, it introduced the reparameterization trick, and it also introduced amortized inference. So basically a very important paper. And it turns out there were even two papers that appeared at the same time. One was by Max Welling, who was actually also a professor at UC Irvine here for 10 years, and another one by DeepMind. And both papers appeared at the same time and had the same ideas. And but the Max Welling paper gets most of the credit nowadays, so for some reason. Okay. Yeah, so how does it actually connect to autoencoders? So it turns out that this idea of amortized inference has a lot to do, is oftentimes almost synonymous with variational autoencoders. And why is that? It sounds like a more general concept. Well, first of all, an autoencoder, as a reminder, is this neural network architecture that essentially goes from high dimensions down to a low dimensional bottleneck layer, which kind of tries to learn a compressed representation of the input. And from there, it's trying to then go back to high dimensions, and it's aiming for minimizing reconstruction error. So it wants to map every data point on itself, every image on itself, while sort of pushing it through a low dimensional bottleneck. And we're hoping that by doing so, we're learning sort of a more general feature representation, a general useful feature representation in this bottleneck. So yeah, so essentially, here's a couple of notations. So x would be the input. Then q of z given x would be the posterior distribution in amortized inference, right? Your variational distribution. But you can really think of it as a mapping, a stochastic mapping that takes X as an input and gets you to this latent Z layer, right? And yeah. And then from there, you're trying to reconstruct the output. And for that, you need a mapping going from Z to X. And that's exactly the likelihood P of X given Z, right? That gets you back from Z to X. So this is like the expression of in particular of variational inference in general, but also of the variational autoencoder. So it can be decomposed in many different ways. So for example, if you add and subtract the prior here, you see actually that there's an equivalent formulation of this evidence lower bound, which essentially no longer involves the joint distribution and its entropy, but in this case, it involves the expected log likelihood and the KL divergence between the variational distribution and the prior, right? So maybe you guys have seen one of the other formulation before. They're perfectly equivalent to each other. Now, it turns out that the second formulation has sort of a closer tie to autoencoders in some sense. And why is that so? Well, first of all, let's see how this autoencoder operates. It takes a data point xi as an input, and then we map that data point to Z using this Q of Z given xi, in other words, the encoder. And from there, we're trying to reconstruct the input x hat by sampling from P of X given Z hat, the Z hat that we've previously generated before. Now, what is actually now the meaning of this training objective? The first term, the expected log likelihood, actually encourages that this mapping be close to the input, right? So here you can actually convince yourself that log P of Z, X given Z, can be thought of as a reconstruction error, right? So you're hoping to kind of, when you start from X to go to Z, you'll go back to X, that you kind of have, that you're very close to where you started off. So the first term actually encourages X hat to be the same as the input xi. In other words, that xi is still likely under P of X given Z hat. Now, the second term is interesting. So at first, you might not be completely clear about what this is actually doing and why it's actually useful. But it turns out it has actually a nice connection to data compression again. And we'll understand that much better in the course of this lecture. Namely, the second term wants these intermediate latent, these sampled latent variables Z hat have a simple form. And in particular, it wants them to be likely under a pre-specified prior P of Z. So it really tries to sort of match what's also sometimes called the aggregate posterior, the collection of all the latent variables, to be well explained by a pre-specified P of Z. Now, this again brings us back to this compression perspective. The autoencoder can be thought of as essentially taking a high-dimensional data point as an input, converting it into a short message, such that a sender and a receiver, and Alice and Bob, can easily, without a lot of redundant information, communicate the content of that high-dimensional input. So if Alice goes on a space mission and needs to send images to Bob, then given like an image xi, we can actually first compress it using this mapping Q going from X to Z. So we sample a Z hat, and this generates a message corresponding to xi. Now you can send that compressed message to Bob, and then Bob can actually use the decoder or the P of X given Z to actually reconstruct that original data point. And it turns out that this scheme works well if the first expectation is large, because that actually ensures that these intermediate messages Zi are informative about X, right? So that they preserve all the relevant information about X, such that you can well reconstruct the input X, right? Don't want to have a lot of loss in that step, right? So the first term wants Z to be informative about X. Now, the second term, the KL divergence between Q and P, actually, again, forces this distribution over the Z's to be close to that pre-specified prior. And the reason why this is useful is that later on, Alice and Bob maybe actually just don't want to transmit these Z's, which are full-length vectors, but they want to use what's called entropy coding and lossless compression on top of it. Right? And for these lossless compression steps, you typically need a model, P of Z, that predicts the density of these latent states pretty well. Right? And therefore, this matching of the of Q to P of Z actually also is important and has an interpretation in data compression. Yeah, as a side effect, if that model once is actually trained, you can now actually generate images. And the reason is that you can simply draw samples from the prior P of Z and just push these samples through the generative network P of X given Z. So that actually allows you to also then generate high-dimensional images. Yeah, there are two questions here. Maybe the back first, and then. Yeah, good question. So the question is, in this compression pipeline, is there an advantage of sampling from Q of Z as opposed to transmitting the most likely observation? Yeah, I was actually intentionally a little vague here. You're completely right. In actual compression, you would not necessarily draw a sample. You would rather transmit sort of the most likely encoding. We'll talk more about connections to actual compression schemes later. It turns out that you even have to discretize these latent states in the meantime. And that has something to do where, yeah, let me get back to that. It's too complicated at this point. All right.
We specified the form of Q, but Q being there to the next time but I don't see where we specified the form of P.
Yeah, that's a good point. So the comment was that we specified that this Q distribution be a normal distribution. We used that in the reparameterization trick, but we never talked about the generative network P of X given theta. And the reason is that this can. Sorry? Oh, the prior P of Z. Yeah, good questions. So in the variational ordering, so in general, for an arbitrary model, it can be anything, right? But for the variational autoencoder in its naive form, you would typically also use a standard normal distribution, maybe with a learned variance.
Where does it appear in the formulation? The form of...
Oh, yeah, good question. Where does this prior appear? Yeah, it's actually always implicitly present in that joint. Yeah, so don't have anything to write here. But usually the elbow is written as this expected joint distribution, right? Expectation under Q of P of X comma Z. And that always factorizes into a P of X given Z times a P of Z. So in a way, it's always there. So it always is already part of the elbow. Yeah.
My question is that when we construct in the network, we only specify, like we only construct the parameters for QZ.
Yeah.
For PZ. So it's like implicitly there, but how do we know it is standard normal?
Yeah. Yeah, so I guess, sorry? Yeah, so that's, yeah, so the question was, how do we construct P of Z? What kind of network architectures does it involve? So really, it's really just a simple normal distribution without any neural networks, right? Because it's a distribution over Z space, and we really pick the simplest thing that we can do. You can make the variational autoencoder hierarchical, in which case you have multiple levels of latent variables on top of each other, and they're all connected through nonlinearities, so through neural networks. In this case, you would have like a more complicated prior. So that also exists, right? And it turns out even for image compression, you typically use these two levels of hierarchical variational autoencoders involving neural networks, yeah, as priors. Yeah, thanks for, yeah, another question here.
Yes, going off a previous comment, why even sort of worry about all this noise? Why not just make Q a delta distribution? Sampling.
Yeah, great question. So why do we even formulate the variational autoencoder as probabilistic? Why don't we just work with autoencoders, right? I mean, why do we clip the variational distribution to be a delta distribution, right? So that would actually in turn lead to a deterministic autoencoder. And the reason is essentially that if you, so here's the interpretation. I mean, first of all, there's a reason why you do that, why you don't do it for data generation. And there's a reason you don't do it in data compression. So when you care about generation, it turns out that if you don't have this KL term, then the empirical distribution of encoded images in that latent state will look highly irregular. So they're not actually looking like a nice Gaussian cloud, but in fact, it's a complicated scattered distribution with many pockets, regions in which no encoded data point exists, and so on, right? And when you then want to generate data, and you, first of all, you don't know which distribution to sample from in that latent space, but imagine you come up with some heuristic to sample, then oftentimes you end up in regions where there are pockets. In other words, you're very far away from any training example. When you then decode these examples, they look not very realistic. So the function of the role of that KL term is to, in some sense, kind of pull everything together. Like all the encoded data points in that latent space should look Gaussian distributed. And this then has the nice effect that when you then sample from that Gaussian distribution with that fixed variance, you always end up in regions where you have similar encoded data points. And so that when you decode, then the corresponding images look realistic. Yeah. And then the answer about compression is more difficult, but there it has something to do that you not only want to have poor reconstruction, but you also want to have a model that models the distribution in that latent space that leads to short code lengths. And we'll also talk about that. In fact, there's actually an expert in data compression from Facebook, Karen Ulrich, who's giving a guest lecture later in the term. So hopefully that's going to be exciting. Any other questions? I think this is actually pretty much the end. Yeah, there's only the summary slide, so feel free to ask questions if there are any. So let me maybe wrap up and then kind of answer questions, maybe also for the people who are offline. So let's kind of summarize what we learned about in the last two lectures, which was about latent variable models. The basic idea of latent variable modeling is that you can build highly expressive, complicated distributions based on relatively simple building blocks. Think of a mixture of Gaussians where you only need individual Gaussians, but you sum over many of them, and that can essentially approximate any complicated distribution. Right? And that's pretty much what the variational autoencoder is doing. And you can think of that as an infinite mixture of Gaussians. The only additional thing is that there are these neural network transformations in between that even improve that property. So once a latent variable model is trained, you can directly generate data by ancestral sampling in this generative process. So you can sample from the prior P of Z. And then for that realized Z, you then can sample from P of X given Z. Right? And remember, both of these distributions were relatively simple. And so you can always generate images using these trained models. It turned out that the tricky part about it was that you cannot simply optimize log likelihood, which is our favorite thing to do usually, right? Simply because the log likelihood is just not available in closed form. It involved that infinite summation over latent variables. And so this was intractable. And as a solution to that, we learned about variational inference that lower bounded that marginal likelihood, right? So it kind of gave us a proxy objective function that we could still maximize. And then we learned that jointly learning a model over theta and inference parameters phi was feasible using this idea of amortized variational inference, which achieved a tractable elbow approximation. And yeah, and then we also learned that the latent variables associated with every data point X can then be inferred in a one-step procedure, just using that trained inference network, just taking that variational distribution Q of Z given X. Actually, I just want to kind of give you briefly survey a couple of ideas here in the next few minutes, and I'll promise to be quick. Just talking a little bit about research directions that are kind of still interesting. So what are the ways in which you can improve variational autoencoders and variational inference in general? So first of all, you can actually improve the optimization techniques used in variational autoencoders. You can work with more expressive variational families, better Q functions, or just kind of coming up with alternative loss functions that might have interesting different properties. And we'll talk a lot about hybrid methods between variational autoencoders and, for example, GANs when it comes to later parts in this lecture. Yeah, this idea of amortization goes actually back to earlier papers. It really makes things more scalable. There are many extensions that have been proposed. And you can also think of it as an implicit regularization of your model. You can also improve the variational approximation, and there are a whole bunch of papers that I just want to point out here. Maybe they interest you, maybe they're relevant for your course projects. Just encourage you to have a look. Some are from our own groups also. You can also improve Q distributions with normalizing flows, which is yet a third class of deep generative models that we'll still talk about. And you can also think about, let me skip that maybe. And think about theoretical properties of these evidence lower bounds. For example, it turns out that tighter elbows do not necessarily yield to better samples. So there are some interesting theoretical works on that. They're also not always leading to informative codes. For example, they're known to fail on text data pretty dramatically. And there's been work on alternative divergences, right? So maybe you want to replace the KL divergence by a different distance measure. There are so-called Rayleigh divergences. There are F divergences. And so there's been a lot of proposed research. Yeah, so with that, I would like to finish for today. So thanks again for your attention. And I'll still have 10 minutes or so if you want to, for any questions that you might have. Thanks. There's the first question here.
Single variable question. So in that reparameterization trick, right?
Mm-hmm.
You can swap the gradient and the expectation.
Uh-huh.
So that's like passing a gradient through an integral, and that I think that can't always happen, right? Are there any conditions that never bother us in like the probability space or
So the question was like whether the gradient can always be pulled into the expectation. I mean, maybe there are certain sort of exotic cases where this might not be possible. I mean, generally, the only constraint really is that the distribution that you take the expectation with respect to should not depend on these parameters. You should not, that distribution should no longer depend on parameters that you differentiate. I mean, that's actually the only limitation that I currently can think of. I mean, otherwise it should always be possible, right? Yeah. See, there may be questions offline. Let's see. Okay, I don't know if there's still. Up to date phi corresponded to 1 through m. M is the number of samples. Yeah, that's right. M is the number of data points. There was another question if an NLP generation related task could be part of the project. Yes, you can do your course projects on natural language processing if you really want to. I generally recommend that you still work with, I mean, yeah, it's tricky. I want everyone to work on diverse projects because that's the most interesting for me, but it's probably easier, honestly, to work with image data just because NLP uses sort of not so many probabilistic techniques nowadays, right? For some reason, deep generative models on language have never really taken over, right? There's not a lot of latent variable modeling there. But on the other hand, like BERT and transformers and all of that, they're still generative models. So you're very welcome to experiment with them if you want to. But if you think about using kind of VAE, scans, normalizing flows, I'd rather recommend sort of visual data to work with. So that's my advice. All right, so and I think that explained it pretty much. All right, well, then thanks again and see you all next week.